Hi guys, let's take a look at a couple of problems here in section 4.3. These are dealing with the first derivative test for finding intervals where our function is increasing and decreasing. The two that have been asked for me to look at with you in this section are 14 and 17 in this video. In 14, we have a cubic function, f of x is equal to 1/3 x cubed plus 13 over 2x squared plus 40x plus 2. In order to do the first derivative test, we take the first derivative. So pretty straightforward here, just power rule. We're going to get x squared for our first term. The 2 comes down, multiplies the 13 over 2 just to give us 13x to the first plus 40. At that point, I knew I needed to set that first derivative equal to 0, so it's better to factor it. So I said I needed to find factors of 40 that sum to get to 13. I said, well, 5 times 8 is 40, 5 plus 8 is 13. Factored it to be x plus 5, x plus 8. We set that equal to 0 to find the critical points. And we know if x plus 5 is 0, we'll get a critical point at -5. X plus 8 is 0, we'll get a critical point at -8. Now we take those critical points along with the understood domain from -infinity to infinity of the original function, and we break up that domain into test intervals. So my first test interval has to go from -infinity to the lowest critical point, which is -8. Then my next test interval would go from -8 up to my next critical point of -5. And then finally, I go from -5 up to the end of my domain at infinity. I choose points to represent each of these regions. You'll see I chose a -10 to represent the first region. Some number between -8 and -5, I chose -7. Some number between -5 and infinity, I chose a 0. Now, all that you have to do with these test points is see how they would affect the sign of your first derivative. Anywhere the first derivative is positive, your function increases. Anywhere it's negative, your function decreases. So you'll notice I chose to put the factored version of the first derivative here for the first derivative sign test. And I said, well, when I plug a -10 in, that first factor would be negative, that second factor would be negative, but I know the product of two negative numbers is a positive. So I can say, well, that tells me that my original function is increasing from -infinity to -8. At any critical point, it's a point where the original function flattens out. So I knew it was increasing from -infinity to -8. It flattens at -8. Then I said, well, what happens from -8 to -5? I'm testing that region with a -7. I can see the first factor would be negative. The second factor would be positive, but a negative times a positive is a negative. That tells me that my original function is decreasing in between -8 and -5. But now, since -5 is also a critical point, it must flatten off at -5. Then I can say, well, okay, what happens from -5 to infinity? It's possible that it would decrease again, but as you can see, it doesn't. The reason it doesn't is because when you plug in the test point 0 into these two factors, both of the factors are positive. And we know a positive times a positive is a positive. Anywhere where the first derivative is positive, the original function is increasing. So it's going to be increasing from from -5 to infinity. Now I can go back to my problem and answer questions. I can see at -8, there's the location of a maximum. At -5, there is a minimum. So back the way that Achieve has it worded, F has a local minimum at, well, the local minimum is at -5. F has a local maximum, clearly at -8. Now I'll erase that a second and then come down here and say, well, now it's asking for the intervals on which my function is increasing, decreasing. Let me bring this back up one more second. And you can say, well, it's increasing whenever the first derivative was positive. It's going to be increasing from -infinity to -8 union -5 to infinity. So I'll have to put that for the increasing, and I'll say, okay, the function is increasing on the interval, the group, from -infinity up to -8. So I'll say comma -8. Then I'll close out that group. And then we say that's in union. So union with the parenthesis, and I might have put an extra space there, so I'll delete that. Union with the group from -5 to infinity. -5, comma, infinity. And we get that one. Now I can say, okay, now the function is decreasing. Well, the function was decreasing only on your only other interval that was between -8 and -5. So I'll put that in here. It's the interval -8, comma, -5. Close that out. This should be the answer. And correct. The next one that there was a question on here was number 17. Let me look at that with you. So in 17, the way I worked that, we have a fourth degree, and this is kind of cool. We have x to the fourth minus 9x to the 3 over 2. And instantly, even though, well, actually the problem did say it too. I started to say the problem didn't say it, but you need to understand that the domain of this problem had to at least be 0 to infinity. Your problem actually stipulates it's strictly greater than 0. They didn't have to stipulate that it's strictly greater than 0. 0 could have existed in our original function, but they have even a more restrictive domain than what I was going to put for it. Anytime you see a fractional exponent, you know square roots are in your problem, so you know x has to be 0 or a positive number. They're saying here that x has to be strictly greater than 0. Okay, now I go in and I take the derivative of that function. I get my 4x to the third minus 27 over 2 x to the 1/2. And then I can say, well, now I know I'll need to set this equal to 0. So since you're going to need to set it equal to 0, you should be pretty thoughtful about how you're going to do that. And so what I'm thinking of here is I know that anything that's factored is much easier to set equal to 0. So I went ahead and I said, well, both terms have a common factor of x. You always pull out the lower power. So you're going to factor out an x to the 1/2 power here. I did that. Whenever you factor out an x to the 1/2 power, that leaves you in the first term with a 4x to the 5 over 2. Please make sure you understand where that comes from. X cubed is the same thing as x to the 6 over 2. You're factoring an x to the 1 over 2 out of an x to the 6 over 2. So of course you have left over an x to the 5 over 2. You're subtracting exponents. 6 over 2 minus 1 over 2 is 5 over 2. In the second one, the x to the 1/2 just cancels out and you have minus 27 over 2. So now we're thinking, hey, this is going to be pretty easy at this point. It's already in factored form. You set your factors equal to 0. I know that the only thing that would make this first factor equal 0, and my problem up here says that x has to be greater than 0, so I don't need to worry about that first factor. The only factor that can equal 0 for non-zero values is the second factor. So I can say, well, set that second factor equal to 0 by setting 4x to the 5 over 2 equal to 27 over 2. Then I divided by 4 on each side to get x to the 5 over 2 is equal to 27 over 8. Then I said, okay, if that's the solution for x to the 5 over 2, I need the solution for x. So what do? I raise both sides of the equation to the 2/5 power. When I raise the left-hand side to the 2/5, I just have x to the first. When I raise the right-hand side to the 2/5, I have my 27 over 8 to the 2/5. Now, Achieve is going to want exact answers in this problem, so we need to keep that, but just to give me an idea of where I would choose test points around that critical point, I went ahead and went to my calculator here, and you'll see where I did it on my calculator. I went ahead and said 27 over 8 to the 2/5, and I got my approximate answer of 1.627 there. So that just shows me approximately where my critical point is at. But now for my test intervals. I say my first test interval is going to start at 0 because that's where my domain starts at. And it's going to go to this 27 over 8 to the 2/5 power. Then I'll go from that critical point of 27 over 8 to the 2/5 up to infinity. I choose a test point in the first region, and here's where that decimal value really helps out. Well, I know 1 is between 0 and this critical point, and between this critical point and infinity, I chose a 3. Nothing special about those numbers other than they are within the regions they're supposed to represent. Excuse me. Now, in this first one, when I plugged in a 1, I knew, of course, 1 to the 1 over 2 power, that's going to be a positive. The second factor, though, pretty easy to plug in. Didn't need my calculator for it. It's going to be 4 times 1, which is just 4, minus 27 over 2. 4 minus 13 and a half. Clearly, that's going to be a negative. So I have a positive factor times a negative factor. My first derivative is negative in this region. So automatically, I showed my original function started at x equals 0. And in fact, it said it had to be strictly greater than 0. So according to the problem, there needs to be an open circle at 0. And then you'd say, well, we know from this right here, it's decreasing from that beginning point all the way up to the critical point of 27 over 8 to the 2/5. And then at that critical point, I needed to test what happened beyond it. So I plugged in a 3. I know 3 to the 1/2 power is positive. It's a little tricky to plug 3 into the second group. So again, I let my calculator assist with that. 4 times 3 to the 5 over 2 power minus 27 over 2. Notice it gave me a positive 48.853. I don't care about the specific value. I just care about the sign. It's a positive. So my second derivative has 2 positive factors in the second region. Thus, it's positive, and thus my original function is increasing. This shows me that 27 over 8 to the 2/5 is the location of a minimum on the original function, and my original function is decreasing before that point and increasing after it. So now let's go back and try to make sure we answer the questions here on Achieve correctly. So I'll say, okay, up first. It says find the x coordinates of the critical point that correspond to the local minimum. So they're already telling you in the problem it's a local minimum. Or actually, if there wasn't any, you'd put does not exist, but there is a critical point that's a local minimum. We'll say it's the entire fraction, and I'll go ahead and put a parentheses and then the fraction. Our fraction was 27 over 8. And we had that raised to the 2/5 power. So I'll say raised to the power, and then in that power, I have a fraction of 2 over 5. Should be gorgeous. Now, the next problem here asks for the location of the local maximum. Well, as you can see, there isn't a local maximum. There's only one critical point, and it's a minimum. So when I go back here to state the local maximum, it specifically says enter D and E if it does not exist, so D and E. Then the function is increasing from that critical point to infinity. So I'll say, well, it's the parenthesis, and let me see if I can just go up in here and copy that. Copy, and I'll come down here and paste it. Yes, makes it much quicker. And then I'll say comma to infinity. And then the function is decreasing from where it began at 0, comma, and I'll paste that back in again. Nice. So the pasting can help you from typing in that complicated fraction each time. Saves a lot of time on this problem. Pretty nice. Let's check that and make sure it's okay. And it is. Hopefully this helped you out with these 2 problems in this section. Let me know if you have any others. I'll be glad to help.